Hi. So let us spend some time understanding what model interpretability is, or rather more popularly known as explainable AI. So, explainable AI is this huge field of research that's currently going on in the area of machine learning and artificial intelligence, and for a good reason. So, today we won't be focusing much on the research part, but rather we'll be focusing on understanding what explainable AI is in the first place. So, before going forward and understanding what explainable AI is, let us first try to understand the difference between machine learning and deep learning algorithms and why they are used in certain situations. So some of the popular machine learning algorithms like logistic regression and k-nearest neighbors are actually quite interpretable. So what I mean by that is in logistic regression, we use a sigmoid curve, and in k-nearest neighbors, we use the distance formula. So once we have these logics in place, we actually pass in our data through these models and we get some prediction on the other side. But since we know what is happening in the middle, we know how this model is interpreting the data and how it is actually reaching the prediction. And that is the explainability part. These models are very easily explainable and can be interpreted by humans. So the flow of these models is like this. We are passing in some data, we are passing them through the model, and then we are getting some prediction on the other side. But we also know what is exactly going in the in-between part. And that's due to the transparency of these models. Now, as transparent as explainable these models are, we cannot use them in all the situations. Instead, many large corporations and institutions use deep learning as their go-to algorithm instead of classical machine learning algorithms. And there's a good reason for it. Deep learnings are extremely complex and they offer pretty high accuracies as compared to traditional machine learning models. And the reason for that is they actually mimic the thinking capacity or the thinking process of the biological human brain. So even though these neural networks offer a very high performance and very good accuracy, there's a trade-off. And that trade-off is the interpretability or the explainability. The explainability is completely lost in this deep learning algorithms such as neural networks. How? Let's try to understand that. Now, before understanding how this explainability is lost, you might ask me a question saying that since these deep learning algorithms, such as neural nets, are derived from mathematical equations, can we not use the same mathematical equation to actually find out what is going on inside them? That is correct, but only partly. So imagine solving a mathematical equation with lots and lots of hidden layers, lots and lots of neurons, and like a million parameters or even more. It would be virtually impossible to solve this using just a mathematical equation that was actually in place for a single layered neural network or a perceptron. Inside this huge network of hidden layers, there are like thousands and thousands of neurons interconnected with each other. So there's a lot of intricacy going on inside the neural network, which is impossible for a human to decode with a mathematical equation. So contrary to the machine learning models, and I mean classical machine learning models, a neural network's architecture follows like this. We pass in some data, and then in the middle, there is this huge black box, which is not interpretable and explainable at all. And then at the other end, there are predictions. Now, you might ask me another question saying that why do we even care about the black box? Why do we care about what's happening in the middle? Why do we care about how the neural network is perceiving the problem or how it is solving the problem or what necessary steps it is taking? All we really should care about is the solution. Well, again, you are partly correct. To explain this, I will take two examples, and these two examples will vary in terms of the implications that problem will have. The first example will be for the Netflix. So Netflix, as you know, uses a recommendation system. So if you don't know what a recommendation system is, so based on your data and the data of other users, Netflix will recommend you a movie or a series. Now, let's say Netflix is using a deep learning neural network in order to identify what movie you will watch or to recommend you a movie. So let's say your watch history consists of spy movies as well as action movies. So based on that, Netflix can probably recommend you, let's say, James Bond. Now that is a good recommendation, or we can say a good prediction of what movie you should watch based on your watch history. Now let's say Netflix misclassifies and recommends you something like Home Alone, which is a comedy movie. So based on your watch history, which consisted of action as well as spy movies, Netflix recommended you something like Home Alone, which is not really a spy or an action movie in any case. So that is a bad recommendation, or we might call it a bad prediction. So what are the implications of this bad prediction or this bad recommendation? Well, there aren't any implications. That's because whatever Netflix recommends me, it's up to me to either watch or not. If Netflix recommends me a wrong movie, I don't really care. If it recommends me the right movie, well and good, I'll watch that. But in case if it recommends me a bad or a wrong movie, well, it does not really have any huge world-bending implications. I'll simply ignore or choose not to watch that movie. So for these types of problems, we don't really care about what is happening inside. All we care about is the predictions, because the implications or the impact of those predictions is not really at a major scale. Now let's take an example where the implications do matter a lot. And that example can be something of a tumor. Let's say a hospital is using a deep learning neural network model in order to identify whether the tumor is benign or malignant. Now, just to provide the right context over here, a benign tumor is something which is not extremely serious, and a malignant tumor is something which is extremely serious. The malignant tumor needs to be acted on very fast in order for the survival rates to go high. So it's the job of the model to identify whether the tumor is benign or malignant. Now there are two types of error that the model can make in this case, and that's a type 1 error and a type 2 error. Let's discuss in brief what these two errors are. The type 1 error is an error in which the model may say someone has a malignant tumor, but in reality, they won't really have a malignant tumor. But let's say the model says that they have. So they will go ahead and get that checked, and then they'll eventually find out that they don't really have the malignant tumor. So no harm, no loss. They got the prediction and they got it checked out and they didn't have it. There's no loss in it. But there's another error, which is a type 2 error, which is actually very serious. In this case, the patient does have the malignant tumor and the model misclassifies the patient to not have the malignant tumor. So in this case, the patient simply ignores that he has the malignant tumor and he avoids getting that checked out. This in turn reduces his chances of survival. Now this is a problem with huge implications. We cannot let this slide by. So even though the hospital has a very good model with high accuracy in identifying which patients have either benign or a malignant tumor, they simply cannot afford to make misclassifications because the implications are very huge and they can cost a life. So in this case, they need to understand how the model is actually making these assumptions or these predictions. In other words, they need to understand and open up the black box to see what is actually going on. Now, this is what model explainability is. Basically understanding what this black box is in order to understand how the model is reaching the prediction. It's not just making a prediction and then using the prediction to solve a problem, but rather understanding how that prediction is being made so as to decide whether it's valid or not. Consider it like solving a mathematical equation. Just by looking at an equation, you cannot really say if LHS is equal to RHS. You need to provide the right steps in order to prove that LHS is equal to RHS. The steps are as equally important as the solution. The model explainability or the explainable AI works in the same way. Basically, you're understanding how the model is making a prediction rather simply blindly trusting the prediction. So that is explainable AI in a nutshell. Now, there are some existing methods that you can use in order to understand how explainable AI actually works, and you can try it on your own datasets. Some good examples of those existing methods might be Lime and SHAP. I've left the links in the descriptions to those. You can check them out if you just want to expand your knowledge or if you simply want to try them out. Explainable AI, as I discussed before, is a huge area of research in the field of AI and machine learning, and something new is constantly popping up, and for a good reason. With that said, I hope this video shed a little light on what explainable AI is, and you can expand your knowledge by reading further papers and understanding more methods on how you can actually interpret these models and how you can explain artificial intelligence better rather than just trusting the predictions that it makes. So if you did enjoy watching this video or if you learned something from it, make sure that you like it and maybe subscribe to my channel, because I'll be making more content based around AI, machine learning, and computer science in general. So it's your cup of tea. Make sure to stick around, and I'll see you in the next one. Bye.